You know those noise-canceling headphones we all love? Ever actually stop and wonder how they do that? It's not just about stuffing your ears with foam. There's something much, much smarter going on. It's an incredible process of creating silence out of noise, and it's all about a machine learning in real time. I mean, we've all been there, right? You're on a super important call, and all you can hear is this weird echo. Or you're on a flight, and that constant drone of the engine just wears you down. The tricky part is, the noise isn't separate from what you want to hear. It's all mixed together. So how in the world does a device untangle that mess? So check this out. This visual really shows the heart of the problem. The signal you want, like your music, and the noise you don't, that engine hum, they're often happening in the exact same frequency range. They're totally overlapping. And that means you can't just slap a simple filter on it to cut out the noise frequencies, because you'd be cutting out huge chunks of your music too. So, if a normal fixed filter is off the table, we need something way smarter. The answer is a filter that can actually change itself, one that has self-adjusting characteristics. We need an adaptive filter. And that word right there, adaptive, that's the key. It means it can learn and adjust to its environment on the fly. Okay, so here's the brilliant idea in a nutshell. The system listens to two things at once: the main audio, which is your music all mixed up with the noise, and a separate reference of just the noise. The adaptive filter's whole job is to take that noise reference and create a perfect mirror image copy of it, an anti-noise signal. When you add that anti-noise to the original sound, the noise and the anti-noise just annihilate each other, leaving you with nothing but the clean music. That is the million-dollar question, isn't it? Because creating that perfect anti-noise isn't some one-and-done calculation. The noise is always changing. You might move your head. It's a dynamic situation, so the filter has to be constantly tweaking its settings to keep that cancellation perfect. So how does it learn what the right settings are from moment to moment? Well, it all comes down to one beautifully simple goal. After the filter does its thing and subtracts the anti-noise, whatever is left over is considered the error signal. Now, in a perfect world, that error would be 0, right? That would mean every last bit of noise got canceled out. So the filter's entire purpose, its only motivation, is to constantly change its own settings to make that error signal as tiny as it can possibly be. To really get how it minimizes that error, let's use an analogy. Imagine a huge surface, like a landscape. Every single point on that landscape represents a possible combination of the filter's internal settings, and the height of the landscape at any point represents how much error that particular setting produces. What you end up with is a performance surface that looks kind of like a big bowl. The perfect settings, the ones with 0 error, are sitting right at the very bottom. The filter's whole job is just to find its way to the bottom of that bowl. So how does it find the bottom? It uses this wonderfully simple and incredibly powerful algorithm called the method of steepest descent. It's an iterative process, which just means it works by taking a whole series of small corrective steps. And the main idea is right there in the name. Wherever you are, you figure out which direction is the steepest way down, and you take a small step that way. Okay, picture this. You're standing somewhere on the inside of that big error bowl, and you're blindfolded. How would you find the bottom? Well, you'd probably feel the ground right around your feet to figure out the slope. Then you'd find the direction that goes downhill the fastest, and you'd take one small step. Then you do it again and again. If you just keep repeating that process, always choosing the steepest path down, you're pretty much guaranteed to end up at the lowest point. And believe me, this isn't just some abstract mathematical idea. The most common algorithm used in adaptive filtering, the one called the least mean square, or LMS algorithm, is a real-world practical implementation of this exact concept. It is the engine that drives the learning in your headphones, in echo cancelers, in all sorts of amazing tech. Now, I know this equation looks a bit complicated, but the idea behind it is exactly what we've been talking about. All it's really saying is that the new filter settings are equal to the old settings plus a small correction. And what's that correction based on? It's based directly on the current error signal. In plain English, the filter looks at the mistake it just made and uses that information to make a slightly better guess next time. It literally learns from its own errors. So you might be wondering, why go through this whole iterative, step-by-step process? Why not just calculate the perfect answer in one single shot? Well, there is a theoretical ideal solution called the Wiener filter, but it's totally impractical for the real world. To use it, you need to know everything about the noise and the signal in advance, and it involves some really heavy-duty math. The LMS algorithm, on the other hand, doesn't need to know anything up front. It just starts at a random spot and starts walking downhill. That's why it's the absolute workhorse of adaptive filtering. Okay, so we know the algorithm will eventually find the bottom of the bowl. But remember, this is all happening in real time, thousands of times a second. So the next really critical question is, how fast does it get there? How quickly does it converge on the solution?
And the answer, believe it or not, takes us right back to our analogy. The speed of this whole process depends completely on the shape of that error bowl.
Now, engineers have a term for this, of course. It's called the condition number. But all that really is a measurement of how eccentric or squashed the bowl is. A perfectly round symmetrical bowl has a low condition number, close to 1. But a long, narrow, oval-shaped valley has a really high one. So why does this shape matter so much? Well, think about it. If the bowl is perfectly round, the steepest downhill path always points directly toward the center, the bottom. The algorithm just marches straight to the solution, super fast. But if the bowl is more like a long, narrow valley, the steepest direction at any point doesn't point down the valley toward the exit. No, it points straight at the nearest, steepest wall. And you can see exactly what happens then. The algorithm takes a step toward one wall, then it has to recalculate. Now the steepest path points to the other wall, so it's forced into this crazy and efficient zigzag, basically bouncing from side to side as it slowly makes its way down the valley. The more squashed that valley is, the higher the condition number, the slower this whole process gets. In fact, we can get super precise about this. The speed is actually governed by this little expression. Now, don't worry about the math itself, just focus on the concept. Think of A as how wide the bowl is along its longest direction, and A as how wide it is along its shortest. If the bowl is really squashed, A is way bigger than A, and that means this whole fraction get really close to 1, and that means each step the algorithm takes is just a tiny correction, which means really slow progress. So let's just quickly recap our journey here. We started with this problem of noise that's mixed in with our signal. The solution? An adaptive filter that learns to create anti-noise by trying to minimize an error. The engine for that learning is the method of steepest descent, which is really just the simple idea of always walking downhill on an imaginary error surface. And finally, we saw that how fast it learns all depends on the shape of that surface. It's really incredible when you think about it. One of the most powerful learning algorithms in modern tech really just boils down to a rule you could teach a toddler. Always take a small step in the steepest downhill direction. It really makes you wonder, where else, in technology or maybe even in nature, are these really complex, intelligent-seeming behaviors actually being driven by surprisingly simple, elegant rules like that?